That's a big word.
Welcome back, everybody. Shout out, Brandon. If you're watching, come in and say the word
Gargantuous.
gargantuous. That's chosen by Luke. Gargantuous. Let's see.
Big.
He just comes in and says big.
He's really sick today. He's not just taking the day
Yeah,
off?
he's actually really sick.
Oh. He just was scared of the calc test.
He's actually sick.
Gotcha. All right. So section 9.1. Actually, all of chapter 9 is about correlation and linear regression. You know how in probably algebra 2, you guys did linear regression, basically taking a yes, you did. Don't shake your head at me, Gabby.
I don't remember doing it. That's the thing.
Well, if you don't remember it, that's okay because we're going to relearn it. But you do this in algebra 2. Actually, I talk about correlation coefficient and how to understand correlation versus causation in my algebra 1 class because it does show up on the algebra 1 OST nowadays. So you might have talked about it a little bit in algebra 1, but we're going to be looking at how do we create those numbers. Like for example, back in algebra 2, you just basically put things in lists and ran the linear regression and just the calculator did the work for you. What we are going to be looking at are the calculations behind what the calculator is doing. Okay, so correlation. There's a difference between correlation and causation, and that comes closer toward the end of the notes. So we have to decide. We have to define what correlation is. Well, if you break down the word correlation, correlate, things that go together, things that relate together. It's a relationship between two variables, between two quantities. If two things correlate, they trend to go together. They tend to go together. The data can be represented by the ordered pairs x, y, where x is the independent or the explanatory variable, and y is the dependent variable or the response variable. Scatter plots can be helpful in trying to determine whether a linear correlation exists between two variables. If you took Honors Algebra 2, you probably did linear correlation, exponential correlation, quadratic correlation, cubic correlation, quartic correlation, done all of those regressions. There's all sorts of regressions that you could possibly do. Sine regression, logarithmic regression, logistic regression, all sorts of regressions that you could compute. And all a regression basically is taking two variables and plotting them and seeing if there is a relationship that you can determine, whether they're both going upward or they're both going downward or they're both trending in the same way. How do they correlate together? How do they relate together? Scatter plots, again, can be helpful in trying to determine whether a linear correlation exists or whether any type of correlation exists. Is something going up while the other thing is going up? Is something going down while something else is going down? Do they both go upward together and then at some point come downward together? What's happening? How do they relate to one another? The first thing that I want to do is remind you guys how to create a scatter plot within your calculators. Okay, so we're going to do that exact same thing. We're going to put this in our calculators here. This is the table that I got out of the book. Old Faithful, located in Yellowstone, is the world's most famous geyser. The duration in minutes of several of Old Faithful's eruptions and times in minutes until the next eruption are shown in the table. So we have duration and then time till next eruption. Duration and time till next eruption. Thinking about it logically, before I even look at the data, before I even see what's going on in the data, if the geyser goes off for a longer amount of time, what do you think is going to happen to the time until the next eruption? Probably longer, right? Because it releases much more pressure. Therefore, it's probably not going to erupt as soon as if it was just a short blast, there's still pressure in there. It's probably going to be not as much time until the next blast, right? Until the next eruption. So let's see if our prediction is correct. Now, to do this, let's go into our calculators here. And again, this might be review for you, or this might be brand new. I don't know whether you've done regressions or not. So I'm just going to teach it like it's brand new. Anybody remember where to go in and put in our data? Stat. And then we edit, right? Hit the stat button and then hit enter on edit. And then we have our list ones and list twos. Now I'm going to delete out what I have in list one. Remember, instead of saying the word delete, I should say clear, right? Because you could actually go up here and delete your list accidentally, and then you'd have to just run setup editor and it'll come back. But don't do that. So hit clear. I just went through that, clear, and then hit down, and then that should clear out everything that was in that list. Right? All right, so list one. I'm going to put the duration into list one, and I'm pretty quick with the number pad here, so that's what I'm going to do. 1.8. Oops, I screwed up. 2.37. 2. Oh. Okay, good. 4.30, 4. Right. Looks like I've got 25 pieces of data. Remember that everything must be paired together, right? You cannot separate X values from Y values. You cannot go out of order, right? If I started with this list, now for my Y values, if I went over here and then copied in here, it would be pairing 1.8 with 79. You don't want to do that. You want to keep 3.78 with 79. So I got to go back over to list 2 and start back from the beginning. Oops, and I just screwed it up. 56. $76, $73, $76. Like the double numbers. Okay. And you just got to make sure you end up 25. Perfect. Okay, good. It's always good to go back and spot check. Just make sure that you didn't, punch the numbers a little bit. Make sure that everything is as it should be, nice and lined up. Like I go back and say, okay, I should see a 4.43 and an 89. 4.43 with an 89. Good. I should see, let me go up a little bit more. I should see a 3.65 with a 77. 3.65 with a 77. Okay, good. Looks like I'm still pretty good. All right. Now, to actually see the scatter plot, okay, if you want to see the scatter plot, remember you go into your Y equals. Click that Y equals button. To see the data, you go up into plot 1. Okay, we're not going to run a regression yet. That'll come soon. I'm just looking at the scatter plot here. To see the scatter plot, you hit enter on plot 1. Right? Now, I'm going to second click onto plot 1, or that Y equals, and I can see what's going to happen with plot 1. Again, I hit second Y equals, and that's going to tell me what plot 1 is doing. I'm going to hit enter up on plot 1, and these are all the different options that I could possibly have. I could see a scatter plot, a line graph, a bar graph, a box and whisker, whatever. And you can actually change the little dots on what they look like as well. And you can even change the list that they're in. Right? We put this into list 1 and list 2. If I accidentally put this into list 3 and list 4, I could go in and change that manually if I really wanted to. But it's always defaulted to go to list 1, list 2. So now, if I just hit graph, it's going to stay on my 10 by 10 window. Am I going to see anything on my window? No. So let's make that a little bit better. I'm going to hit zoom. And at the very bottom of my screen, zoom 9 is zoom stat. Okay, zoom stat. That's going to give you your scatter plot as a nice, neat graph. Okay. Come on. Come on over. Come on, baby. You can do it. Come on.
Froze. Double click.
Oh.
That worked.
Okay. But here's my scatter plot. Do you see a correlation?
Goes up.
Yeah, I see a correlation, right? As my X is increasing, what's happening to my Y? My Y is increasing as well. Is that what our prediction had said? As I increase the duration, is the time until the next eruption increasing as well? Yeah. As x increases, y increases. And I see some sort of linear trend, right? I can see some sort of correlation in here. And what we can do now is if you see some sort of correlation and you create an equation that models that situation, you can then predict the future. You can then predict things that may happen in the future. Okay. And that's where we're headed. Obviously, does this appear to have a linear correlation?
A little bit.
Yeah, I would say yeah. As x is increasing, y is increasing, right? Now, what's the difference between this correlation? Let me do this. Let me be real fancy here. Let me go white.
Well,
And here, okay. Is that a, what did I do there?
You made it more direct.
yes.
Yeah, I made it have a stronger relationship, right? The strength of relationship was increased.
It's like taking out outliers, right?
Yeah, what if I do that?
Real strong.
Super
An
strong.
even stronger relationship, right? So how do we tell the difference between this linear relationship and this linear relationship? Obviously, this is a weaker relationship than if I had covered all those outliers up, right? So how do we tell the difference between the two? Well, that's what we have as the correlation coefficient. Look at that.
Oh, no.
No.
You know when you put it down, it's actually not that bad.
Look at that. Now, you don't need to write that down.
When you take it down, it's actually not
What
that
did I
bad.
just look at?
Just taking some of it.
Now, here's what we're going to do. I would never make you memorize that. First of all, it's on your chapter 9 formula sheet in here. Look, it's right there. And for our purposes on any assessment, you're allowed to use your graphic calculators, and you can compute that on your graphic calculators. Okay. If we want to actually use an objective measurement of the strength of correlation, we want to calculate the correlation coefficient. Now, this is the calculation of the correlation coefficient. Your calculator does this for you. And I'll show you how to find it in your calculator. But please appreciate what the calculator is doing for you. Okay? Appreciate what the calculator is doing for you. Let's analyze the actual equation a little bit, though. Okay, n. What is n? The number of things, the number of pairs that I have. So in my Old Faithful example, it was 25, right?
Yeah.
Okay. So we would have 25 times, what's that mean again?
So,
The sum of all the x times y's. Okay? So this is the number of pairs that I have times the sum of all the x times y's. So I would take 1.8 times 56, 1.82 times 58, 1.9 times 62. Add all those up. That's sum xy. Oops, sorry, I don't want to do that. I want to go here. Minus, okay, this is interesting, the sum of x's times the sum of y's. So it's actually, shouldn't this be pretty close to this? Yeah. There might be some variation, and if it was a perfect variation, what do you think the top would come out to be? N. Just n, right? Okay. So there might be some variation in sum xy minus sum x times sum y, right? But this is just the sum of all your x's together times the sum of all your y's together. Okay, and that is divided by, okay, we got n times a square root of n times x squared minus the sum of x's squared. And again, if this was a perfect correlation, what do you think I would have here? N, right? These two things would cancel. We would just be left with an n. So the square root of n, right? And so let's kind of jot that down. Jot that down, not necessarily you jot that down. But if this was a perfect correlation, we hypothesized that we would have n on top. This was a perfect correlation. Okay, and then we would say, well, if this is a perfect correlation, sum x squared would probably be the same as sum x squared. Right? This is squaring all your x's and then adding them together. This is adding all the x's and then squaring them, multiplied by n. But I still have this underneath a radical, right? Okay, look here. Aren't I doing the exact same calculation with the y's?
Yeah.
Sum of all the y squareds, right? Square all the y values, add them up, minus the sum of all the y's squared, multiplied by n. So what do you think is going to end up if this was a perfect correlation? Square root of n. What is the square root of n times the square root of n? N.
What?
What is n over n?
What?
And isn't 1 a perfect correlation?
Yes.
A perfect positive correlation, right? So that's where we're coming from with this R value. R being the level of strength, right? And we'll talk about the parameters of R here soon. Now, the population correlation coefficient is represented by this. Now, this is sample correlation coefficient, right? R value, lowercase r, is sample correlation coefficient. We sampled eruptions and times on Old Faithful, right? But when we talk about population, that's talking about all of them, right? All possible eruptions. Could we ever study all possible eruptions of Old Faithful? No, because time is infinite, right? Well, time is all relative. Goes back to our earlier conversation. Now, population coefficient, correlation coefficient, is represented by, anybody know what that is?
P.
Weird P.
Weird P.
Standard deviation.
Sideways.
Now,
80 degrees.
what was the symbol for standard deviation? It looked like this, right? What was that called? Sigma, right? What is sigma again? Sigma is just a Greek letter, right?
Yeah.
Likewise, this,
Pigma.
not pigma. That is just a Greek letter. That's really funny. That Greek letter is called rho.
Whoa.
Rho. It makes the R sound in the Greek language. So if you see that symbol, it would make a R sound.
They missed a lot.
Greek doesn't roll their R's. Greek language doesn't roll their R's. So this would be rho, the R sound, if it was in a Greek word. Now, how does this relate? Well, just like, this was population standard deviation, right? What was sample standard deviation? Lowercase s. Right? So likewise, rho is population. Population. This is population correlation coefficient. Our R value is sample correlation coefficient. I'm trying to abbreviate, and it's not working out very good. So likewise, if I'm talking about a population, it's usually a Greek letter. What does population mean? What symbol represents population mean?
Is that the X bar?
No, that's sample mean, right? X bar is sample mean.
It was mu.
Yeah, it was mu, right? Which is another Greek letter, right? So we're in this same mode of, if you've got a Greek letter, it represents something usually about population. If it's a English letter, it's representing something about a sample. Okay, so rho is population correlation coefficient. R is sample correlation coefficient.
They didn't have samples in Greece.
Apparently not. Right. Okay. Now parameters on R value. Okay. The range of any correlation coefficient is between -1 and 1. Right. -1 and +1. If it's close to 1 or at 1, well, at 1 would be a perfect correlation. Right. If it's close to 1, it is a strong positive linear relationship. If it's close to -1, it is a strong negative linear relationship. So 1 is a strong positive, -1 is a strong negative. 1 is a strong positive, -1 is a strong negative. The closer you get towards 0, the weaker the correlation gets. The closer you get towards 0, the weaker the correlation. If a correlation coefficient comes out to be 0, it is perfectly spread apart, perfectly scattered.
Are you okay?
Correlation.
No.
So again, 1 is a perfect positive linear relationship. -1 is a perfect negative linear relationship. The closer you get toward 1, the stronger it gets in a positive direction. And the closer you get toward -1, the stronger it gets in a negative direction. And what do I mean by direction? All I'm talking about is the slope of the line. Now, once you get past linear regression, once you get like going into quadratic or cubic regression, there's no more line, right? There's no more slope. So what you look at is just how closely those points fit to that line. In the calculation of R, you actually talk about R squared value when you go into quadratic and cubic and quartic or exponential regression. It transfers from an R value to an R squared value. Now the R value, when I square it, it's always going to be positive, right? So that's why if you square it, that's why once you pass through linear regression, you never talk about anything being negative anymore. It's always positive. And that just means how close it is toward that line. The only negative R value that you ever possibly have is when we're talking about a linear relationship. Okay. The book gives this diagram. I mean, it's just a visual example of the same thing. -1, there is a perfect negative correlation. 0, there is no correlation. And 1, there is a perfect positive correlation. I like this diagram a little bit better because it shows examples. It shows examples. Let's take a look at each one of those. Our first example there, the number of adult ticket movie prices as it compares to total cost. Should there be any variation? If there is, then that's a shifty movie theater, right? So number of adult movie tickets and total cost should be a perfect positive relationship, right? As I increase my X value, as I increase the amount of tickets I have purchased, the total amount that I need to pay is going to increase at a linear rate. Perfect linear relationship. Now, perfect positive relationship, I should say. Okay, height in inches and shoe size. What would you expect to see? As I increase height, what do you think is going to happen to shoe size?
Bigger shoes.
Yeah. Now, does that always happen?
No.
Not necessarily, right? Is there some variation? Yeah. And that's why you see a strong positive correlation, but not a perfect positive correlation. There's a strong positive correlation, but not a perfect positive correlation. This R value would turn out to be 0.81. It's going to be necessary for you guys to be able to look at a set of data, look at least a graph, and be able to predict what you think the R value is going to come out to be. This is a weak positive correlation. They say anything below 0.5. Actually, interestingly enough, the state test for Algebra 1, because our Algebra 1 students have to do this exact same thing. They have to be able to look at a set of data and be able to predict an R value and predict whether it's going to be a strong positive, strong negative, perfect positive, perfect negative, or weak. Our state test says anything below a 0.6 is considered weak. Anything below a 0.6 is considered weak. Our statistics book considers anything below 0.5 weak. There's no set rule. So weak positive correlation would be R value of 0.45. We can see some sort of general trend in the upright direction, but not necessarily, there's a lot of different variations on where I could put my line. And then I have some negative relations, right? Number of incorrect answers and your score on the test, right? Let's assume this is like a multiple choice test, right? Where all of them are the exact same amount. Number of incorrect answers and then exam score. perfect negative correlation, right? If they're all the same amount, okay, 1, 2, 3, 4, 5, 6, 7. As I go, my score is going to decrease steadily. Take a look here. Number of absences in test grade. The more you are absent, what trends to happen with your test grade? It usually gets worse. Are there anomalies to that? Of course there are. Strong negative correlation, negative 0.92. No correlation, IQ score and height. IQ score and height. You know what this it kind of looks like an S, doesn't it?
S curve.
Is an S curve? All right. Okay. Doing these calculations by hand can be extremely time consuming. So let's go in and actually see how we do this in our calculator, shall we?
Please.
So I'm changing up the data. Let's go into our stat and hit edit again. Let's clear out our lists. I'm going to hit clear when I'm up on top of list 1, and then I hit down. Do not hit delete. I'm going to go up on list 2. I'm going to hit clear, and then I'm going to hit down. All my data's gone.
So what'll happen if you do hit delete?
You just have to go watch here. If you, my marker. Everybody watch here real quick. If you accidentally delete a list, okay, say, well, I'll do it. Here, stats, edit. I'm going to delete list 1. I'm up on here, and I accidentally hit delete. List 2 starts with list 2. Right? If you ever do that, it's a really quick fix. You hit stat, and you see setup editor. Just hit that, run the program, and now it kind of like resets it back to default.
Oh.
Okay.
So let's enter our X's. 1, 3, 5, 6, 8. And let's enter our Y's. 7, 10, 12, 13, and 16. Now, before I actually run my linear regression, let's do the scatter plot real quick. I'm going to go into my Y equals. My plot is on. Good. And then I'm going to go down to zoom 9. For me, that's zoom stat. You might have more zooms that you could use, but go to zoom stat. What do you see?
It's like perfect almost.
Almost.
No.
Is it going to turn out to be exactly 1?
No.
No.
0.99.
It's going to be something pretty close, right?
Yeah.
It
You need to
did.
do it 10 times. It's going to be something pretty close to 1, but it's not going to be exactly 1, right? We know it's not going to be negative, right? Because I see a positive slope. All right. So now let's actually figure out what my linear regression is going to be. You go stat, scroll right once to calc, and then here are all of our regressions. Okay. We see 4, 5, they're all regressions. Linear regression, quadratic regression, cubic, quartic, and then we got which is weird. Why did they have 2 different ones?
BX.
AX and BX.
You get the same thing.
Oh.
That's
Like
true.
you get the exact same numbers.
So it
They're
doesn't
just
matter?
ordered different. No.
Well, it seems
We'll
like it
test
wouldn't.
There's natural log regression. There's exponential regression. There's a power rule regression. A logistic regression. Yeah. Signed regression. All sorts of fun stuff. Let's go back up to choice. Was it 4?
Let's just
Yep.
random.
Linear regression.
Linear regression. Now you might have to go hit enter a couple more times because it's going to ask you. The newer calculators say, do you want to use list 1 and list 2? And you just, yes, you want to use list 1 and list 2 because that's what you plugged in. All right, so here's our information. Now, does anybody not see the R squared and the R value? Yeah. Let me show you something. If I reset my calculator, or if your batteries die, and I want to hit yes, not no, 7, 1, 2. Okay, my calculator has been reset.
No.
Okay. If I go, oh shoot, that means I gotta re-enter my data. Whatever. Easy. 1, 3, 5, 6, 8, 7, 10, 12, 13, 16. All right. Okay. Now if I go stat calc 4, I don't have an R value. Right? My R squared and my R value is gone. Okay. To turn it back on, you just go into catalog. You're looking for diagnostic on. You could either just scroll down until you get to your D's for diagnostic on, or if you just hit the green D button, see that? It's the matrix next to the -1 button. But if you hit D, it'll jump to all the D's. and you want to just find diagnostic on, and that'll turn your R value back on. Okay. I don't know why it's not defaulted to always be on. I think that's
Enter twice.
yeah, because now this is the program, and then you have to run the program. Okay, it's done now. Now if I go stat calc 4 again, now I have my R values back. So if you ever don't see it, just turn your diagnostic back on. Second catalog, D for diagnostic on, run the program, and they should be there. What do you notice about your R value? First of all, I don't care about my R squared value for the linear regression. What do you notice about your R value?
Close to one.
It's very
Very close to 1, 0.996, which makes sense because this is a very good linear regression, right? A very good linear regression. 0.996 is to be expected. Now, let's take a look at our actual equation. Y is equal to AX plus B. A in this case is, we'll round it to the nearest hundredth, 1.24x plus 5. Well, if I round to the nearest hundredth, that would be 5.90. There is my equation. 1.24x plus 5.9. Now, if I plug in each one of these x values, is it going to give me the exact y value that I have in the table? No, because it's not a perfect correlation. Like, for example here, if I plug in 5, is it going to give me exactly 12? 1.24 times 5 plus 5.9. No, but it's going to give me something super close, right? Very, very close. And the higher the R value, the closer it gets, right? And I think that one, let's see the second one, 3. 1.24 times 3 plus 5.9. Yeah, 9.62, so 0.4 off, 0.38 off, right? So the further out those pieces of data are, well, then the further out, the further off your y value is going to be, based on your prediction. And at this point, then we can say, well, what if my x value is 10? We can, keep the data going. Right? There's, I don't think we talked about it here, but there's a difference between extrapolate and interpolate. Extrapolate is to mean look past the data, look beyond the data. Interpolate is to look within the data. So if I said, okay, give me the x value at 15. What's the y value when the x value is 15? That's called extrapolating, going beyond the parameters of the data. If I said, okay, notice how I don't have the x value of 7 or 4. What if I said, okay, give me the y value when x is 4. Give me the y value when x is 7. It's interpolate, look inward. Interpolation. Did we talk about that here? I don't think so. No. Let's stop there.
Yeah.
Because now we start doing hypothesis testing based on this.
No.
So much fun. Yeah, no. Woohoo. All right, here we go.
Any last